Are you trying to better understand standard structural systems to help you select which structural system is ideal for your architecture project? Or are you just wanting to better understand standard structural systems for the ARE? Well, let's explore these systems. Architecture is not just about crafting eye-catching designs, but also about ensuring these designs can stand tall and firm. That's where the understanding of standard structural systems is essential to becoming an architect. These structural systems serve as the backbone of any architectural design, and are what make our buildings safe and stable. They're the unsung heroes that hold up the magnificent structures we admire in our cityscapes. Whether it's a humble home or a towering skyscraper, every structure relies on these systems. Understanding them allows architects to design not just with aesthetics in mind, but also with a keen eye on functionality and safety. It empowers them to push boundaries, to innovate, and to create structures that are as durable as they are beautiful. So are you ready to delve into the world of structural systems? Now let's dive into standard structural systems, starting off with wood. In the realm of architecture, wood is primarily used for one-way structural systems. This means loads are transferred along one direction only. Now let's delve into some common terms. First up, plank and beam framing, a method where planks provide a deck-like platform and beams serve as the main support. Next, we have glued laminated construction, or glulam. This involves gluing together layers of lumber to form a single, stronger piece. Lightweight eye-shaped joists are another wood-based structural system. They're designed for strength and are often used in floors and roofs. Trusses, box beams, and stressed skin panels are also essential. Trusses are triangular frameworks used to span or support structures. Box beams, on the other hand, are hollow beams often used where weight is a concern. Lastly, stressed skin panels. These are high-strength, lightweight panels used in floors, walls, and roofs. That's a brief rundown on wood. Next up, we have steel. Steel is known for its strength and versatility in architectural structures. Let's dive right in and unpack the key structural systems that utilize this robust material. First up, we have beam and girder systems. This system comprises beams, also known as girders, which support smaller beams, or joists. The primary girders bear the load, transferring it to the columns, while the joists support the flooring above. It's a hierarchy of support that brings efficiency and resilience to the structure. Now, let's talk about open web steel joist systems. This system is a lightweight steel truss assembly used primarily for roof and floor support. It's known for its high strength-to-weight ratio and its open web design, which allows for easy installation of electrical and mechanical systems. Both these systems highlight the remarkable flexibility of steel in architecture, offering solutions that combine strength, efficiency, and ease of installation. That covers the basics of steel. Moving on to concrete. Concrete, a staple in architecture, offers a great deal of flexibility. This material is commonly used in two different forms: cast-in-place and precast concrete construction. Cast-in-place concrete is poured and cured at the construction site, allowing for a wide range of shapes and designs. Precast concrete, on the other hand, is cast off-site and transported for installation, offering speed and precision. Beyond these basic forms, there are several specialized concrete construction methods. Tilt-up panels, for instance, are large concrete slabs cast on-site and tilted into position. This technique combines the strength of cast-in-place concrete with the efficiency of precast systems. In terms of structural systems, concrete offers one-way and two-way systems. One-way systems support loads along one direction, while two-way systems can bear loads from two perpendicular directions. Beam and girder systems, a type of one-way system, are composed of beams that support smaller joists. Concrete joist systems, on the other hand, use parallel joists to support slabs. Flat plates and flat slabs are similar in that they are both two-way systems that support loads without the use of beams. However, flat slabs have drop panels for additional strength at the columns. Waffle slab systems, named for their unique grid-like appearance, are particularly efficient for larger spans and heavy loads. Precast structural members such as single T and double T beams are cast off-site and installed later. These members are efficient for long spans and can be used in floor and roof systems. Post-tensioned concrete is another noteworthy method. It involves casting concrete around flexible tendons, which are then tensioned after the concrete has cured. This technique allows for longer spans and thinner slabs while reducing cracking. Concrete is indeed a versatile material. Now let's talk about masonry. Masonry structures, known for their durability, come in three basic types. The first type is the single-withe construction. which involves a single layer of masonry units. This design provides a balance between strength and cost-effectiveness. Then, we have the double-withe construction, essentially two single-withe walls tied together for added strength and stability. Finally, the cavity wall construction, which includes an airspace or cavity between two withes, offers superior moisture protection. Now let's discuss some key terms. The slenderness ratio, which is the effective height to thickness ratio of a wall, is vital in determining the wall's buckling load capacity. Flexural rank refers to the resistance of a masonry wall to bending or flexing. Lastly, fire resistance ratings are measurements of a wall's ability to resist fire spread. These ratings are determined by the type and thickness of the masonry units used. Having covered masonry, let's move on to composite construction. Composite construction involves the combination of two or more materials to resist loads. A prime example of this is reinforced concrete construction, which ingeniously combines the compressive strength of concrete with the tensile strength of steel. Let's break it down. Concrete, as we know, is a fantastic material under compression. It can withstand a great deal of force pushing down on it. But when it comes to tension or pulling forces, concrete falls short. That's where steel comes in. Steel is excellent under tension. It can resist a lot of force pulling it apart. So, when we embed steel bars or wires, known as reinforcements, within the concrete, we create a composite material that can resist both compressive and tensile forces. This is the basic principle of reinforced concrete construction. That sums up composite construction. Next, we'll look at walls and the building envelope. While non-bearing walls might not be part of a building's structural systems, they play a crucial role. Imagine a building as a living organism, with the structural system as its skeleton and the walls, or the building envelope, as its skin. This skin is responsible for protecting the building and its occupants from the onslaught of the elements, but how does it support its own weight and how does it handle the exterior loads, particularly wind, without damaging the facade? For the weight of the envelope itself, the building's structural system steps into play. The envelope is connected to the structural frame at various points, enabling the weight to be evenly distributed across the building. This distribution helps prevent any undue stress on one particular area, thereby maintaining the integrity of the envelope and the building as a whole. Now let's talk about how the envelope handles exterior loads. Wind, for instance, is a powerful force that can exert a tremendous amount of pressure on a building. The building envelope needs to transfer this wind load to the structural frame without causing any damage to the facade. This is achieved through a combination of careful design, selection of appropriate materials, and strategic placement of connections between the envelope and the structural frame. Think of it like this. When the wind hits the building envelope, it's like a wave crashing against a cliff. The cliff doesn't crumble because it's designed to withstand such forces, and the same goes for a well-designed building envelope. The wind load is transferred along the envelope, through the connections, and into the structural frame, which disperses it throughout the building. So, while non-bearing walls may not bear the weight of the building, their role in supporting their own weight and managing exterior loads is crucial. They act as the first line of defense against external forces, protecting the building and its occupants. Remember, every element of a building, from the structural system to the building envelope, is interconnected. Each plays a vital role in creating a structure that is not only aesthetically pleasing, but also structurally sound and safe. That brings us to the end of our journey through standard structural systems in architecture. So, why is understanding standard structural systems in architecture important? It's because every successful architectural design hinges on a sound grasp of these systems. Each system, be it wood, steel, concrete, masonry, composite construction, or the building envelope, plays a crucial role in ensuring structural integrity and safe design. Mastering these systems will give you the ability to create buildings that are not only aesthetically pleasing but also structurally sound. Recognizing the unique characteristics and applications of each material, their strengths and limitations, can help you make informed design decisions that balance both form and function. Moreover, understanding these systems is critical in preparing for the Division III, Programming and Analysis test of the Architecture Registration Exam. It's a stepping stone towards becoming a licensed architect, a testament to your technical knowledge and professional competence. Remember, a great architect is not just a great designer but also has a great understanding of the technical aspects of buildings. Please, deep learning, keep growing, like this video, and subscribe to this channel.